So this is more or less a review. And let's see, for posterity and recording sake, number one, gases generally have what? Low density, high density, close packed particles. No increase in volume when temperature is increased, no decrease in volume when pressure is increased. Process of elimination. They change volume with temperature and they change volume with pressure. Right, so we can throw those out. Closely packed particles. I don't think so. Those particles are way, way, way far apart as compared to what? Liquids and solids. They're way far apart. Plus, there's a lot of distance between them compared to how big they are, each particle. Lots of space. High density? Obviously not if they're not close packed particles. So it has to be A, right? They are low density. Right? Low mass, large volume, right? Based upon, so you make that real small, make this real big, and you get low density. How about 2? What's pressure? What is pressure? Right, let's just define it. Force per unit area, right? Okay. Is there anyone that fits that? Probably this one right here. We'll do the easy ones first. What's the SI unit for pressure? Nobody remember? Well, if pressure is force per unit area, effectively it's force in newtons per unit area, square meter, but we give that a special name. Actually, all I have to do is say that. It's the Pascal. Pascal is the standard unit for an SI unit for pressure. And the reason it is because it's convertible. If a Pascal equals 1 Newton per square meter, then we can put it in this formula or that formula and units will cancel. If you try to put atmosphere in there, it won't work because atmosphere is atmosphere and nothing else. So that's one of the, I don't know if you call it beauties of, but the functionality of the SI system is that all the units are interconvertible, some form or fashion. Okay. A glass column is filled with mercury. Where's this one going? Inverted in a pool of mercury. Right, so you have to put your thumb over it and submerge your hand in the mercury. You have to do that, otherwise it won't work. The mercury column stabilizes at a height of 729 millimeters above the pool of mercury. 729 millimeters. What's the pressure of the atmosphere? Okay, this is a word problem. And word problems are designed to confuse, right? So they throw in all this extra stuff in here, which isn't necessarily confusing, but it does tell you that what you're dealing with is a barometer. And this is the height of the mercury column. And the answer, it has to be in atmospheres. So what kind of problem is this really? That's unit conversion. That's all it is, pure and simple. Right, so we can cancel the mercury and leave us with atmospheres. So now all we need is a conversion factor. Right? 1 atmosphere is equal to how many millimeters of mercury? 760. And that's in useful information in case you're worried about memorizing. So 760 and 729 is less than 1, right? So let's see, can we reason this one out? Well, maybe not. It's not going to be that one. It's not going to be this one. It might be one of these. So we might have to do the calculation after all. 729 divided by 760. 0.959. Okay. Is that the right number of significant figures? Yeah. This is a conversion factor. Right? That's an exact number, so you don't have to worry about it. This one has 3, so that one has 3. Okay, that was number 5. Let's see, can I page down? Yeah, we get 6. Local weather forecaster reports that the current barometric pressure is 30.4 inches of mercury. 30.4 inches of mercury. What's the current pressure in atmospheres? Do we have a direct conversion for inches of mercury in atmospheres? It should be in useful information. Anybody remember what it is? No, no such law. 29.92 inches of mercury equals 1 atmosphere. So we just divide that out. And this is less than that, so it's got to be greater than 1, but not much greater. So it's either A or C. Can't be C because they're not exactly the same number, so it has to be A. You can reason that out. You don't even need your calculator. Okay. Let me know if I lose you. Okay. But that's not my purpose. I may drag you along kicking and screaming, but I don't want to lose you. Number 8, the air pressure in the inner tube of a tire. On a typical racing bike is held at a pressure of 112 psi. That's because they're little bitty things like that. I had a 10-speed once. I think the pressure on that one was like 65 psi. So I could hit bumps in the road a lot more efficiently than a racing bike. You do that with a racing bike, you got a bent rim. Okay, so what are we looking for? Convert to atmospheres. All right, so we need another one. What does PSI stand for? Pounds per square inch, right? Okay, and we need to convert it to atmospheres. Right, so how many PSI are in 1 atmosphere? No clue? 14.69. Okay, so we divide that out, and it should be 7.62. Does that seem reasonable? Okay. That's reasonable. Let's see, atmospheres. Okay. The next couple of ones are actually just defining laws. What's Boyle's law? Well, let's put it in the formula. Right? What is the formula for Boyle's law? Pressure times volume is a constant, right? So if pressure goes up, volume goes down, and vice versa. All right, so which one of these statements fits that? Let's see. The volume of a fixed amount of gas is inversely proportional to its pressure at constant temperature. Yeah, B. Inverse. Remember, anytime you have a product of 2 variables equal to a constant, it's always inverse. If that's constant, if one of these changes, The other one has to go the opposite direction in order to keep it constant. What's the other? I think 10 is Charles' law. No, it's Avogadro. Well, Avogadro works. Avogadro is what relationship? Moles and is it volume? I think it's volume. Or is it pressure? I think it's volume. Yeah. So that's Avogadro's law. If the pressure is constant, temperature is constant, and you shove more gas in your cylinder, the volume is going to go up, right? So you increase the moles, you increase the volume. So whenever you have a quotient of two variables equal to a constant, they're always a direct relationship. All righty. There's Charles' law. Getting ahead of myself. So Charles' law is what two variables? Volume and temperature. And that's a constant. It's a direct relationship. So that should be C. The volume of a fixed amount of gas is directly proportional to its temperature in Kelvin at constant pressure. And remember, whenever you're dealing with temperature, unless you have a specific reason to use Celsius in calculations, convert to Kelvin. Yep.
Is the coffee print?
Oh, I can go look. Talk amongst yourselves.
The pressure? Yes. I feel like we just took a test. We're just I feel like there's a shit I could say at least. Wasn't it supposed to be? I think it's supposed to be fun. He said he did it again last week. I thought there was the buffer. There's just so much on this. I tried to do the homework. Did you try that? The homework for chapter 5. Was it all edition? This is all it's exactly. Yeah, I did that. Finished. It wasn't as bad as yeah. Yeah, I think there's initially had I could have gotten papers. So that like thanks for that. But not the answers. Just well, I hate that. And I have to work for them. Obviously, if you're going to support this, we're going to have to support yeah. I'm going to raise your I'll just resend that you were excited about the system. I think the only thing that really saved it was the was. I'm hoping that you can on this one. I don't I'm not that confident in saying obviously. I hope there's yeah. Maybe I feel like we talked about it now. Maybe. And I'm thinking that so we don't have to do it. We did, we talked about it. We only have one class in the thing. And there's like the really have one class, but I think there was this There's no point. But chapter 6 is supposed to be
Printer was out of paper. So I just decided to wait. Okay, now we can get back to, we did Charles. Okay. How about? No. Too far. No, not too far. I went too far. Did I go too far? 15? Is that the next one? Oh, you don't know because you don't have the highlighted one. That's good. Gaseous chlorine. Gaseous chlorine is held in two separate containers at identical temperatures and pressure. This, you don't need to know this to solve the problem, but how do we write gaseous chlorine? Right? That's gaseous chlorine because it's one of the diatomics. Okay, two identical separate containers, identical temperature and pressure. We don't know what their volume is yet, but they both have the same temperature and they both have the same pressure. All right, both got chlorine. The volume of container 1 is 1.3 liters and contains 6.7 moles. Okay. The volume of container 2 is 2.33 liters. How many moles? All right, so that's the question. How many moles are in that one? All right, sometimes it helps to draw a picture. Helps me anyway. I try to keep it all in my head. So how do we solve this problem? What kind of problem is it? Remember when I was talking about gases? There are basically two types of problems: before and after, and state. Is this a before and after or a state? It's a before after. Right? You got these two values, those are constant. These two values, then you got these two, but one of them's missing. Right. Liters, liters, moles. Moles is what we want to know. All right, so whose law are we going to use? About Avogadro. We just talked about that one. So this one is equal to this one. Right. Now, if you don't draw a picture, then what you need to do is set up a list here. Like that. This is your unknown. You got values for these and put them in there where they need to go. Then when you plug them in the equation, you won't put them in the wrong place. All right. So all you have to do is just fill in the data now. 1.3 liters divided by 6.70 moles. And this one is 2.33 liters divided by that. And solve for your n. Right? So n comes over here. And this one goes over here. This goes over there. So it's 2.33 times 6.7 divided by 1.3. Will give you your answer, which should be 12 moles. Now, as the last step, you ask yourself, does that make sense? Right? If you started off with 6.7 moles and not quite double, you didn't quite double the volume, what should happen to the number of moles? The moles should double also, or not quite double, which, yeah, that's reasonable. Okay, do a check on yourself, right? Because if you do a calculation and it comes out to 0.12 moles, you may want to rethink your calculations. Right? Is it reasonable? I told y'all the mechanical engineering story, didn't I? About my friend at LSU. Oh yeah, he was he said this happened in several courses, but students they'd be studying a certain type of mechanical engineering, whatever they do, chapters. And then they'd have a test on it. And they'd have tunnel vision for the formulas that were developed in that chapter. And they take the information that's given in the problem and cram them into those formulas and come out with the wrong answer. And they wouldn't think about asking themselves, is this answer reasonable? Like the answer should be in the neighborhood of 12.5 newtons, say, force. And they come out with 12.5 times 10 to the 6th newton. And you just wouldn't dawn on them. Well, they wouldn't know how to fix it before the test was over. That's more likely, I bet. So, is the answer reasonable? Let's see. Go. Get out of the way. Okay, 18. Oh, yeah, I'm already taking up too much time. Body temperature is 309 K. Is it really? What is body temperature in Celsius? I didn't tell you that one. 37. Right. So 273. Ooh. That person has a fever. Oh, no. No, they don't. Sorry. Forgot to carry my one. So they're okay. Okay, now what's the question? On a cold day, what volume of air at 276? All right, so this is inside the person, temperature person. And outside the person is 276. Okay, all right. So they've already changed the temperature for us. That's good. With a lung capacity of 2.2 liters, what volume of air at this temperature must the person draw in to fill their lungs at that volume, 2.2 liters. The trick to this problem is getting your values in the right place, right? This volume is associated inside the body with that temperature. And this volume is outside the body at that temperature, right? So before and after a state. Before, after. Two temperatures, two volumes. So what law are we dealing with? Volume and temperature. There's a person, there's the outside. So you just plug in the numbers. Okay? If you don't actually draw the picture out, sometimes it helps to get a mental picture of what's going on. Just picture yourself outside at that temperature, which would be what? 3 degrees Celsius? It's kind of chilly. Just above freezing. Any questions about that? No, we're good. Let's see, the answer should be 1.97 liters. Is that reasonable? But yeah, if you draw in a volume of 1.97 liters and then heat it up, it should fill that space. Okay, I'll go with that. All righty, 20. You're holding 2 balloons, an orange balloon and a blue balloon. That's an orange and blue. I don't know what their volumes are yet. The orange balloon is filled with neon. And the blue balloon is filled with argon. Okay. The orange balloon has twice the volume of the blue balloon. So that's okay. I'll go with that. So this volume of neon is equal to twice the argon volume. That's the way you write that. Which of the following best represents the mass ratio of this one to that one? Okay, we want to know the mass of the, I should say orange, is what ratio to the mass of the blue? All right. So what's the difference here? Well, neon, what kind of information do we have? All the information we need? Not from that problem. If you're going to compare masses, all we've got is just volume and what's the gas. If we're going to compare masses, we need to know something about each one of these. Right? So we go to periodic table, right? So the mass of neon is about 20. About argon, it's about 40. Okay. So if we had, let's just suppose we had equal volumes, right? If the volumes were equal, what would the mass ratio be? If they were equal, then this would be 1 and that would be 2, right? Right? If the volumes are the same, then you'd have the same number of particles. So the only difference is the ratio of the masses of each particle. So they'd be 1 to 2. But this one is half the volume, so it has half the number of particles, right? So what does that tell you? It's 1 to 1. You got half the number of particles, but they weigh twice as much. Did I lose anybody? 1-to-1 ratio. Now, I think in the work problems, I go into all kind of mathematical gyrations. But since I've made out that work problems thing, I think this rationale works better for the students than to try to ask you to dredge up your math skills. I mean, it works both ways. All right. Let's see. We're gonna skip a few. Must be a lot of repetition. Okay. Ooh, got another one. That's good. Okay, 29. A gas sample is heated from -20 to 57, and the volume is increased from 2 to 4. If the initial pressure is 0.14, what's the final pressure? Okay, first of all, is this a before and after or state? It's before and after. But you got more than just 2 befores and afters. You got 3 befores and afters. So that tells me that we're not going to be using one of the specific laws like Boyle's or Charles or Avogadro's. We need the combined gas law because we've got 3 variables in here. And what's the combined gas law? P1 V1 over N1 T1 equals P2 V2 over N2 T2. That's your combined law. Okay, so let's ask ourselves, can we eliminate any of these? Which one stays the same before and after? Moles. All right. So this is before, this is after. So a gas is heated from -20. Oops, in the wrong place. From -20. We haven't changed units yet. To 57. Okay. And the volume is increased from 2 liters up to 4.5 liters. The initial pressure is 0.14 atmospheres. And this is the unknown. Okay. So now that we've got our variables assigned, what's the next step? Change that to Kelvin. Right, so this will be 253, and this will be 330. Okay, and then solve for P. Okay. Now, if we did everything right, our answer should be 0.0811 atmospheres. So the pressure dropped. Okay, if we go from volume of 2 to 4, the pressure should drop. And if we go from -20 to 50, or 253 to 330, that's in the denominator. So it gets bigger, and that makes the quotient also get smaller. If the denominator gets bigger, the quotient gets smaller. So that seems reasonable. Okay. We shall move to the 30. All right. A sample of oxygen gas has a volume of 1.72 liters at 27 degrees Celsius and 800 total. How many oxygen molecules does it contain? What kind of problem is this? It's our first one. It's a state problem. We're only given these values Not before and after, but what is it right now? So volume is equal to 1.72 liters at 27 degrees. Right, so we're going to have to add 273. And what else are we given? Pressure. 800 torr. What's a torr? Did we mention torr in the lecture? Okay, a torr is a millimeter of mercury. That's all it is. So this needs to be converted to atmospheres if we're going to use right, because this value, the units of this value dictate what these have to be. And if we use this one, liter atmospheres per mole K, that tells us the units. All right, liters good, atmospheres not good. That'll give us atmospheres. Moles, that's going to be our answer. And K, that's 300. Okay, so now we have all our values. We just plug in pressure, volume, temperature, and the ideal gas constant, and solve for N. And that should be the answer we're looking for. No, that's how many molecules. Okay, so this will tell us how many moles. I guess I'm going to have to do that. So pressure times volume, 1.72 liters, and pressure is 800 divided by 760, which is 1.053. Okay, well, times that one. Yes. Okay. Now we want to divide by this one. Right? We multiply those two, divide by this one, and divide by this one, which is 300. Okay. So this is the number of moles is 7.35 times 10 to the minus 2 moles. Okay, how many molecules is that? We need a unit conversion now. Moles, molecules. What's the magic number here? Starts with an A. Avogadro's. 6.022 times 10 to the 23rd. And that's 4.43. Is it 27? Yeah, two significant figures, so we're going to say 4.4. Times 10 to the 22 molecules. I bet we didn't use the proper number of significant figures in that answer, but that's the closest one. And I guess since this says none of these, you could say none of these. But when I'm grading it, my key probably says this one, or if in this situation. So if I grade it wrong and you say, yeah, but it's only got two significant figures in it, you can come argue for your points. Okay. All right. We've got a half hour left. Let's see, I'm going to have to free up that here. That's good. 37. Which conditions of pressure, temperature, and moles, respectively, are most ideal? pressure, temperature, moles. Now, this is just memory, right? In order for a real gas to behave ideally, what conditions work? Low pressure, right? High temperature, low moles. So pressure, temperature, they're all in order. So we need low, high, low. Low, high, low. Here we go. Okay. Let's see. 40. 41.1 gram sample of neon gas exerts a certain pressure in a container of fixed volume. What mass of argon is required to exert half the pressure at the same conditions of volume and temperature? So we're given 41.1 grams of neon. And we want to know the mass, what mass of argon. So this is the mass of neon. What mass of argon? What mass of argon is required to exert half the pressure? So in order to exert half the pressure, we need half the number of moles of argon. So we got to find out how many moles this represents before we can say anything about argon, right? Okay, so 41.1 grams of neon is how many moles? Moles over grams or grams over moles means what? Molar mass. 20.18. So that'll tell us how many moles of neon we actually have. (41.1) divided by 20.18 is 2.037. 37 moles of neon. And we want to exert half the pressure, so we need half the number of moles. So divide that by 2. 1.018 moles of argon now. Did I lose anybody? That many moles exerts a certain pressure. This many moles of argon exerts half the pressure. Okay. Now we need to convert that to mass. All right, so argon is actually 39.95. Now I get 40.7 grams of argon. There it is. Okay. Did I lose anybody? All right. Okay. Let's bring this one down. Scroll. Move too far. Keep it right on. Let's go. 49. For which gas are the molecules diatomic? You don't even think about this one much. Diatomic means there's 2 atoms, right, in the molecule. The only one that fits is chlorine, right? Okay. That's too easy. I have a few easy ones in there. To deflate the pressure during the exam. All right, 52. The mass of 1.12 liters of gas Y, volume of Y, is 1.12 liters at standard temperature and pressure. What's standard temperature for a gas? 0 degrees Celsius. Well, I can say that, which is equal to 273 Kelvin. Okay. What's standard pressure? 1 atmosphere. And we find that the mass of this gas under those conditions is 6.23 grams. The molar mass of the gas Y is what? All right, well, what's it asking? It's asking us for the molar mass, which I do the molecular weight. It's just because I'm old. That's the way we used to write it. Molecular weight is mass per mole. Right? We got the mass. What we need is the moles. Right? So how many moles do we have? Solve for moles. Right? And then put in the numbers. 1 atmosphere, 1.12 liters, R 0.08206. I'm going to leave out the units because there's no there for it. And temperature is 273. Okay, so that gives us the number of moles. 1.12 divided by 0.08, 206, and 273. So that's 4.9. Oops, rounded off. 5 times 10 to the minus 2 moles. So we see 6.23 grams per 5 times 10 to the minus 2 moles is what? 125 grams per mole. And there it is. Oh, wait. I started off looking at this problem and went to this one. Okay, so this was 53. Sorry. Get ahead of myself. So let's do 52. Let's see, we get to keep this information up here. So it's the same problem. Well, the same conditions. It's a different answer. Okay, let's see if we can figure out the density. So what's density? Density is mass per unit volume. This one's even easier. There's the mass, grams, there's the volume. Oops, we usually report what? Oh, well, this is a gas, so grams per liter is accurate. Grams per liter is common for gases because you need more volume to give you a measurable amount of gas. Okay, so we don't have to change the units, 1.12 liters. So what's that about? 5, in the neighborhood of 5? 5.56 is the closest one. That's the answer. Grams per liter. Let's see, if we had a liquid, what would the units, common units be for a liquid? Grams per milliliter. How about a solid? Grams per cubic centimeter, or cc. But these are exactly the same. Okay. So that's what I get for working backwards. And let's down here and scroll a little bit. Where is it? There we go. There it is. Oops, there's another one. Can I get them all? No, I can't get them all. Let me go back down. So I can page next time. There we go. 55. Argon has a density of 1.78 grams per liter at standard temperature and pressure. How many of the following gases have a density at SDP greater than that of argon? So the density of argon at standard temperature and pressure is equal to 1.78 grams per liter. So what do we need to compare? If they're all at standard temperature and pressure, and we're talking about 1 liter, that they've all got the same volume too. So what's the difference among these? They're molar masses. That's all we have to compare, the molar masses. Which ones have a greater density? Which ones have a greater density than argon? So let's just compare the molar masses, right? What's the molar mass of argon? Argon, chlorine, helium, ammonia, and nitrogen dioxide. Okay, so argon is 39.95 grams per mole. Chlorine is 35.45 times 2. 70.9. Right, there's a good candidate. Helium is about 4. Ammonia, 14 plus 3 is 17, roughly. Approximately. And 14 plus 32 is what? I can't do that in my head. $46. Okay, so how many of these are greater than argon? That one. That one. 2. That's why the answer is C. 2 of them have a greater density than argon at the same temperature, same pressure, and the volumes are fixed because we're ratioing everything to 1 liter. Right, so all we have to compare is the molar masses. Right, because they're going to have the same number of moles in that volume. So the only difference is how much does each one weigh? And there you have it. Okay. That was 55. Let's see. Oops. There we go. Which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample at constant volume and temperature? That's 56. The relationship graph of pressure versus molar mass. So pressure versus molar mass. All right, so if we're gonna graph these, how does molar mass vary with pressure? If the temperature is constant, the volume is constant. So this is constant, and this is constant. If the volume and temperature are constant, then as the pressure goes up, 1 gram sample. 1 gram sample. So what does that mean? It's only 1 gram sample of a gas. Different gases. See that? Different gases. So how do these different gases vary? These different gases vary by the mass of each particle. So if volume is constant, temperature is constant, the number of moles is constant. Because we have a 1 gram sample of the gas and it doesn't vary. Right? So the number of moles is constant also. Did I lose anybody on that one? Okay. So if we've got the same number of moles at these conditions, then what will increase the pressure? Constant volume and temperature. Constant volume and temperature. 1 gram sample of different gases. Okay. So how does the pressure vary with the molecular weight? If the molecular weight increases, 1 gram sample of each, that's our limit. So if you have, let's look at like practical. A 1 gram sample of neon would be a certain number of particles. But if we increase the mass of argon, it would take fewer particles, wouldn't it? Right? So as the molecular weight goes up, the pressure would have to come down because we have fewer particles. Right? So that's an inverse relationship. It ought to look like Boyle's law. And none of those fit. You need a hyperbola. And those are all straight lines. I don't feel real comfortable with that, my explanation. Did I lose anybody? So I would be surprised. I mean, I understand it well enough to take an exam myself and get the problem right, but I don't know if I explained it well enough for you to do the same. That's my problem. Okay. Let's see. All right, 58. Given the reaction, 2 ammonias plus 3 chlorines yields 1 nitrogen and 6 hydrogen chlorides. You react 5 liters of ammonia with 5 liters of chlorine measured at the same conditions in a closed container. Calculate the ratio of pressure in the container after versus before. All right, so let's see. What do we know? We know this is our reaction, and they're all gases. So I'm not going to write gas. Okay. All right. 5 liters of ammonia and 5 liters of chlorine. Okay. Measured at the same conditions in a closed container. Okay, I assume that the same conditions they're talking about is volume is constant, temperature is constant. Moles will vary, right? Because you're starting off with 5 on this side, you ended up with 7 on that side. But this is not a stoichiometric mixture. Right? You have exact amounts of that, exact amounts of that. So what does that say? One of them's going to run out. So how many moles do we have here? I'll tell you what. I want to see if I'm overthinking this. The ratio of pressure, final pressure versus initial pressure. Okay. So the pressure, the initial pressure is 10 liters of gas. Right, so the volume is initial is 10 liters of gas. In the interest of time, I want to see how I work this problem. Okay, I used a bunch of algebra. We do have to figure out which one's doing it. Let me come back to this one, because it depends on whether we've got time enough to work it. This is going to take some time to work this one. So let me hold this off camera. We'll come back to that one. We have time. We don't have time. I'll work the problem on the board after class and put it in the recording. Because I don't want to eat up every last second we have. We've only got 10 minutes left. We have to go in the lab, right? 1:45? Yeah, okay. Yeah, I think the best course would be to move on and come back to that one. Okay, this one might be doable pretty quick. 0.72 grams of a liquid. Grams of a liquid is vaporized at 110 degrees. So that's mass. Temperature equals 110 degrees C. We're going to have to say that because it has to be in Kelvin. And the pressure is 0.967 atmospheres. The gas occupies the volume of 0.559 liters. The empirical formula of the gas is CH2. CH2. What's the molecular formula? So we need our multiplier. All right. So what are we missing here? We got the mass. What we need is the number of moles. Right? Because we need to know the molar mass of that gas after the multiplier. Okay, so we need the number of moles. Let's see. PV goes on the bottom, and N RT goes on the top. Oops, sorry. Can't have them both places together. Nope. Backwards. There we go. EV is N RT. That's right. Okay, so pressure is 0.967 atmospheres. Volume is, here it is, 0.559 liters. R is 0.08206. And temperature is 383. Okay, so that's the number of moles. Point 967, 0.559, we go with the 206 divided and 383 divided. So the number of moles is 1.72 times 10 minus 2 moles. So the molar mass is that mass divided by this moles. 0.72 grams divided by 1.72 times 10 minus 2 moles. Oops. This was simple. There we go. 41.9 grams per mole. Okay. So what do we got to compare? If that's the true molecular weight, molar mass of our gas, of our compound, what do we need to compare to it to find this number right here? We need the empirical mass. What is that? 12.01 plus 2.02. Plus 14.03. Compare that to 41.9. That'll give you X. Right? This is the true molar mass. This is the empirical mass. So I need to divide that into, yeah, it's already there. So to the nearest whole number, X equals 3. So we have C3H6. Okay. Did I lose anybody? Where we were headed? Gotta find that number. How do you find that number? You ratio the true molecular weight to the empirical weight. Okay. We can get the empirical weight just by adding these up, but we have to calculate that one. When you calculate the molar mass, you need the mass for a given number of moles. You got the mass right here. So we had to find the number of moles. Right there. Okay, that was my reasoning for the whole problem. All right. Time for one more. I'll look at that. Look at this document and see how many more. Got to go. 8. Ooh, got a long way. Second one, I have to come back and do more than one. You post them in video because I don't want to eat up your lab time. We can do this one before we leave. If M is the molar mass, M is the molar mass, R is a gas constant, okay, T is the temperature, P is the pressure. Which one of the following expressions represents the density of a gas? Okay. This takes a little algebra. Everybody remember your algebra? Okay. Which represents the density of the gas. So density is mass per unit volume. Okay. What else do we have to go on? Molar mass. M equals mass, right? Same as mass over here, per unit volume. Oops. Per moles. Sorry. What else do we know? We also know the ideal gas equation. PV equals nRT. Okay, we need to get something equivalent to density using these three equations. Okay, These have a common variable right here. Okay, so if we solve this one for n equals PV over RT and substitute that in here, what do we get? We get mass over PV divided by RT. So if we simplify that one, then remember the denominator of the denominator is the numerator. So this one flips up here and we get MRT over PV. Okay, so what do we have in common over here? Well, now we have, well, actually we have two possibilities. This one is here, and this one is here. So it looks to me like M divided by V, right there. If we solve this equation, and forget this part, we solve this equation for, well, I've got M over here. Then we could take P up here and RT down here. And that's equal to M divided by V. So now we can substitute this. Actually, this is equal to density. Okay. And that's this one right here. PM over RT. Anyone. One way to isolate metals from their ores is to react the metal oxide with carbon as shown in the following reaction. Here's our balanced equation. React with carbon yields what? The free metal plus carbon dioxide. Okay. If 34.08 grams of metal oxide, 34.08 grams of metal oxide react with excess carbon. That's good. That means we don't have to have a limiting reactant. This is going to be all used up. And 4.37 liters of CO2 is formed at 100 degrees C and 1.5 atmospheres. What's the identity of the metal? All right, that's the question. What is the metal? Okay, what do we need to know to identify the metal? Only two things can tell you what that metal is. If you know the atomic number of protons, you can identify the metal. Where are we going to get the number of protons out of that? You can't. So next best option is, what's the molar mass of the metal? So the molar mass of the metal is what we're looking for. So in order to get the molar mass, we need mass per moles. Okay, what do we have so far? We've got the mass, right? So we got that part. Now we need the moles. How many moles? Excuse me. No, we don't have the mass yet. We don't have the mass yet because that's the mass of the metal oxide. Yeah, that's the mass of the metal oxide. What we need is the mass of the metal. Okay, let's work on the moles first. How many moles of that are there? Okay, so how do we do that? Well, we need some stoichiometry, right? We have a balanced equation. If we know how many moles of carbon dioxide there are, then we can say that there are twice as many moles of metal. Right? So we have volume, we have temperature, we have pressure. We can find moles because we have the equation for it. Right? Number of moles then is equal to PV divided by RT, which is equal to pressure, 1.5 atmospheres, that's good. Volume, 4.37 liters. About R, 0.08206 liter atmospheres per mole K. And temperature, 100 plus 273. Okay, so now we can figure out how many moles there are. All right, so let's say 1.5 times 4.37 and divided by 0.08206 and then 373. Right. So I get 0.2146 moles. That's of CO2. So how many moles of metal do we have? Twice as many moles. So we have 2 times that, or 0.4283 moles of metal. Okay, so we got this much. Now we need the mass. You know what would be simpler, I think? We know how many moles of M we have. Since it's 2 to 2, that means that's the same number of moles of this. What if we figure the molar mass of this right here? What will be the molar mass of MO? Molecular weight of MO equals 34.08 grams per 4283 moles. Where's my calculator? Here it is. 34.08. And I get 79.57. 79.57 grams per mole. Okay, that's the molar mass of this compound. How much does the metal contribute to that molar mass? Whatever's left over from the oxygen, right? We're told that it's 1 metal and 1 oxygen. So how would we get this if we were to calculate it? If we were to calculate that value, we would take the molar mass of M plus the molar mass of oxygen, and that would give us this value. So what we're saying is, the molecular weight of MO is equal to the molecular weight of M plus the molecular weight of O, because there's 1, 1, and 1, right? Do we know enough? Well, we got this one is 79.57. What's the molar mass of oxygen? 16. Molecular weight of metal is that. So now we have an equation in one unknown. So we can say the molecular weight of M is equal to 79.57 minus 16. And that's equal to 63.57 grams per mole. Okay, now how do we find that? go to the periodic table and look for 63.57 or the very closest one you can get to that. The closest one we can get is copper. Which is C. It took a little detective work. A lot of detective work, actually. All right, that was 81. And let's see, who's next? 82. All right, this is just memory. 82. What's the standard temperature for gases? 0 degrees Celsius. B. What's the standard pressure for gases? 1 atmosphere. That's B also. All right, we're going to have to. Oops. Oh, can't do it. I can't do it. There we go. Next one, 86. All right. 142 milliliter sample of gas is collected over water at 22 degrees C and 753 torr. What's the volume of the dry gas at standard temperature and pressure? The vapor pressure of water at 22 is 20 torr. Okay. Remember that description I gave you of using Dalton's law of partial pressures, where we collected a gas over water, and once we've collected the gas, we know that the pressure of the gas plus the pressure of the water vapor is the total pressure. So let's say, what do we have? 142 milliliter sample of gas. So the total volume is equal to 142 milliliters. The temperature is 22 degrees C. This is the temperature over the water. And 753 torr. Total pressure, 753 torr. What's the volume of the dry gas at STP? All right. So let's find out the pressure of the dry gas first. So the total pressure is equal to the pressure of water vapor plus the pressure of the gas. Okay? So that means we need to know what this one is and subtract it from that one. And we're told that 22 degrees, it's 20 torr. Right? So the pressure of the gas is equal to 753 minus 20, which is equal to 733 torr. Okay, that's the pressure of the gas at 22 degrees. What we're looking for is volume. What's the volume of gas? All right. This is the pressure. This is the pressure of the gas at 22 degrees. Okay. This is the temperature of the dry gas at 22 degrees. Okay. The temperature, this is the initial temperature. This is the initial pressure. This is the initial, the volume. Right. The initial volume is 142. Okay, we have a multiple problem here. Okay, this is going to be the initial pressure of the gas, 733. This is the initial temperature. This is the initial volume. Now we need final volume, which is the question. Final temperature, which is 273 or 0 degrees Celsius. And then the final pressure. Yes, STP, standard pressure, is 1 atmosphere or 760 torr. Okay. Now, what are we working with? P1 V1 over N1 T1 equals, and let's be consistent here. Initial. P final, volume final, over N final, T final. Okay. What's not going to change? The moles are not going to change. The moles of the dry gas are not going to change. We have initial pressure, initial volume, initial temperature here. Final pressure is 760. Final volume is the question. And final temperature is 273. Okay. So all we have to do is insert the values. Initial pressure, 733 torr. Initial volume, 142 milliliters. Initial temperature, 295. No. Final pressure, 760. Final volume, that's the unknown. And then final temperature is 273. There we go. Okay, now we just have to solve for this one, right? This one comes over here in the numerator, that one comes over here in the denominator. Do the calculations, and you should end up with, oh, none of these. So we have to calculate it. Okay. All right. 733. One times 142 divided by 295 times 273 divided by 760. Okay. 127. 127 milliliters. That's right. It's not there. 127 is none of these. It was an 86. All right. 88. Oxygen gas generated by the reaction 2 potassium chlorate yields 2 potassium chloride plus 3 oxygen is collected over water at 27 degrees in a 1.55 liter vessel at a total pressure of 1 atmosphere. The vapor pressure of water at 27 degrees is 26 torr. How many moles of KClO3 are consumed in the reaction? Okay, this is a stoichiometry problem. So 2 KClO3, which is a solid. Heat it, you get 2 KCl plus 3 O2 gas. Okay. Let's see, what do we know? What do we know? The question is, how many moles of this So how do we do that? We want to find moles of this. Well, we're given information that pertains to a gas. So we're going to have to use gas laws somehow to get moles of this. Once we get moles of oxygen, we can get moles of potassium chlorate. All right, so what are we given? We've got a total pressure of 1 atmosphere. Right? But that's a mixture of oxygen and water vapor. So the pressure of water vapor is 26 torr, right? And this is 760 torr minus 26 torr would be the pressure of O2. Right? 760 minus 26. 734 torr. Okay. I think we're probably going to be using the ideal gas equation. So this is going to have to be converted to atmospheres again. Nine, 6, 5, 8 atmospheres. Okay, that's the pressure of the oxygen. Okay, it's the pressure of this one. Okay, what else do we need? We need temperature. Temperature is 27 plus 273 equals 300. Okay, pressure, temperature, volume. The volume of a vessel is 1.55 liters. Okay, now we have what we need. PV equals nRT. N equals PV over RT. So the number of moles of oxygen is equal to pressure, 0.9658 atmospheres, volume, 1.55 liters, 0.08206 for R, and temperature, 300. So that'll be the moles of oxygen. Again, 6.08 times 10 to the minus 2 moles of O2. Okay, now we know the moles of O2. How do we get the moles of KClO3? Coefficients, right? That's in the numerator. Denominator, numerator. So we have a 2 here and a 3 there. So 2/3 of that value. 4.05 times 10 to the minus 2. Okay, value is given in standard notation. So let's move the decimal to the left, 2 places. 1, 2. 0.0405. Right here. That's how many moles of KClO3 were consumed in this reaction. All right, that was 88. Let's see, I'm going to have to scroll a little bit. Okay. 94. The valve between the 2-liter bulb in which gas pressure is 1.8 atmospheres and 3-liter bulb in which the gas pressure is 3 atmospheres is open. So we've got, let's draw a picture. We got the 3-liter bulb connected to a 2-liter bulb. This one has 3 liters, 2 liters. What else do we know about it? 1.8 atmospheres in the 2-liter bulb. And in the 3-liter bulb, we have 3 atmospheres. Okay. What's the final pressure in the 2 bulbs? Temperature remains constant. All right. For this one, we're going to need 2 different laws. We're going to need Dalton's law of partial pressure, and we're going to need pressure volume, Boyle's law. But the trick is this. Assume, and it doesn't matter what the gases are, they could be the same gas or different gases, doesn't matter. Assume we're going to take this one as evacuated. There's nothing there. So what happens when we open the valve? Right? Rushes in, we calculate the new pressure. We calculate the new pressure if this is a vacuum. Then we say, if this is a vacuum, what happens if we open the valve? Open the valve. Now we get a new pressure. Well, what's the total pressure? The total pressure is the sum of the pressure from one plus the pressure from the other one. So we need 2 Boyle's law calculations and then take those results and add them together in Dalton's law of partial pressure to give us the final value. Okay. So let's take this one and say that's a vacuum. So pressure 1 equals 3 and volume 1 equals 3. Pressure 2 is unknown. Volume 2, what's volume 2? Volume 2 is 3 plus 2 because we're going to open the valve and let it push into that vacuum. So this one is 5. Okay, now we can calculate what is the P, P2. All right, so we have P1 V1 equals P2 V2. We're solving for P2, so P1 V1 over V2. P1 V1 over V2. Okay, so we have 3 times 3 divided by 5. So that's 9 divided by 5. That's 1.8 atmospheres. So if that's a vacuum, then the final pressure in here of this gas is 1.8 atmospheres. Okay? Now let's do the other side. Now we have P1 equals 1.8 atmospheres. V1 equals 2 liters. P2 is unknown, and V2 is what? It's the same as before. It's the same 5 liters. Okay, so now this is going to be equal to P1, 1.8 times V1, 2, divided by 5. So 2 times 1.8 is 3.6 divided by 5 is 0.72. Okay, that's the contribution from this side into that space. The total pressure equals 1.8. Yeah, that's a zero. 1.8 plus 0.72. $2.52. Okay. So this was Dalton. Excuse me. This was Boyle. This was Boyle. And this was Dalton. Okay. 94. All right, let's 95. Partial pressures of CH4, methane, nitrogen gas, oxygen gas, and a sample of gas were found to be 135, 508, and 571 millimeters of mercury, respectively, for each one of those. What's the mole fraction of nitrogen? Okay. So methane had a partial pressure of 135. Nitrogen had a partial pressure of 508. And oxygen had a partial pressure of 571. So how do you calculate the mole fraction? Recognize that the number of moles are directly proportional to the pressure. Right? So we can equate these to the mole values, which means that the partial pressure of nitrogen is equal to 508 divided by 135 plus 508 plus 571. .418. 0.418, right there. So the trick to this problem is to remember that the ratio of pressures is the same as the ratio of moles. Dalton's law of partial pressures. All right. The total pressure is equal to the sum of all the partial pressures. Let's see which one fits that. Equal amounts, volume, fixed amount, no. Directly proportional, no. Total pressure of mixture of gases is the sum of the partial pressures. D. D is the correct answer for this one. Let's see. Yeah, that one came up. 103. Calculate the root mean square velocity for oxygen molecules in a sample of oxygen gas at 11.8 degrees C. All right, for this one, the root mean square velocity. Let's see. How do they list that? Okay, they use a mu for oxygen. The root mean square velocity for oxygen. And this formula is in useful information. So it's the square root of 3r, let's see, 3r 3RT divided by the molar mass, I believe. Yes. Okay. So the care we need to take with this one is to make sure the units match. Notice that R here is given as joules per K mole. Well, remember that joules is an SI unit. So we have to use standard SI units for everybody else. Right? R, okay. Let's see, temperature, 11.8. So the temperature is going to be 11.8 plus 273. Okay. So that's 284.8. Okay. Okay. Oxygen molecular weight is what? Well, oxygen is 16, so two of them is 32. But that's grams per mole. Right? Mole is standard. We need kilograms per mole. So if that's grams, then kilograms is going to be 1,000 times smaller. Remember, if the unit gets bigger, the number gets smaller. So we go 32 times 10 to the minus 3 kilograms per mole. And then R is given. Okay, now we can calculate. Right? 3 times R, 8.3145, and temperature is 284.8. Molar mass, 32 times 10 to the minus 3. Okay, so let's see what the root mean square velocity is. 8.3145, 284.8 times, and then 32 exponent minus 3 divide, and then take the square root of that. Okay, I get it. This is going to be in standard units also. 4.71 times 10 squared. Meters per second. Well, let's see. It's in standard units too. Okay. 471 meters per second. Now, which one's closest? That one right there. Okay, the trick to this one is not just knowing the formula, but recognizing that you're using a different R and changing the molecular weight or the molar mass to match the units of SI. All right, 103. Let's see. 109. Okay. So to answer 109, we have to remember what are the postulates for the kinetic molecular theory of an ideal gas. Which one of these is included as a postulate? Okay. So these may be valid statements anywhere else, but we've got to find which, if any, are part of the kinetic molecular theory. The distance is not small. The distance is very large. That was false. All collisions are elastic. That one's true. Average collision between molecules, both molecules have the same kinetic energy. Oh, no, that's not true. They don't have to have the same kinetic energy. The average kinetic energy for the whole mix is a value, but each one doesn't have to have the same kinetic energy. We have a mix. Okay, so that was my mistake. This one is also false. And D, all molecules are move randomly in zigzag directions. We don't know that they zigzag. They move in a straight line until they smack into something. Right, so that one's false also. All right, so B is the only true one in that group, because they do not have the same velocity. Graham's law. All right, remember what Graham's law said. The Graham's law refers to how fast a molecule moves from one place to another, and relates that to the molar mass of the gas. We call that the rate of effusion or the rate of diffusion. A molecule with a higher molar mass will move slower than one with a smaller molar mass at the same temperature. So which one talks about rate of effusion? Let's see. No rate of effusion there. Here it is. The rates of effusion of gases are inversely proportional to the square roots of their molar masses. That's Graham's law. Let's see. Let me scroll that one. Maybe we can get two on one page. Okay, here we go. 116. Hydrogen and chlorine gases react to form hydrogen chloride. You and a friend are on opposite sides of a long hallway. At opposite ends of a long hallway is what they should say. Okay, you or I have hydrogen, your friend has chlorine. You both want to form HCl in the middle of the room. That should be in the middle of the hallway. Which following is true? Okay, so we got a long hallway here. And we've got somebody here. And we've got somebody here. And one side has, oops, excuse me, hydrogen gas, right? Yep. And this one has chlorine gas. We want these to come together and form HCl right there in the middle. Okay? So which of the following is true? Well, let's look at the possibilities. You should release the hydrogen first. Your friend should release chlorine first. Both should release at the same time. You need to know the length of the room. You need to know the temperature to answer this question. All right, we can eliminate two of these right off the bat. You don't need to know the length of the room. Right? Any length of room will do. You need to know the temperature to answer this question. No, because they're both at the same temperature. Temperature doesn't matter. Not as far as the ratio goes. So we're looking at these. Both release the gas at the same time. What would happen if you released it at the same time? Which one's going to move faster? Hydrogen. Hydrogen will be over here somewhere. By the time chlorine gets there, that won't work. What if you release hydrogen first? If you release hydrogen first, it's going to travel even farther before you release the chlorine. That won't work. You need to release the chlorine first. Give it time to travel a certain distance. Then when you release hydrogen, they'll meet in the middle. That's the answer, B. Picture works good for this one. 117. Okay. Order the following in increasing rate of diffusion. Rate of diffusion. That is how fast the thing moves. So which one moves faster? The fastest is the lightest one. The slowest is the heaviest one. The highest molecular weight, or the molar mass. So we need to figure out, use Henry Ford. What's the molar mass? And we don't have to get these exact. We just need to have enough accuracy in our calculations to tell them apart, right? So fluorine is about 19, so that's 38 grams per mole. Chlorine is 3545, so that's like 71. NO, 14 plus 16 is 30. 14 plus 32 is 62. No. Let's see, 32 and 14 is 50. Right? Yeah. 46. And methane, 12 plus 4 is 16. Okay. Those are sufficiently different, we can tell them apart. All right. In following an increasing rate of diffusion, so the fastest one is the lightest one. So the lightest one is going to be this one, right? So this one's going to be on the far right. The next one is going to be NO. The next one is going to be F2. The next one is going to be NO2. And the last one is, oops, excuse me. There we go. That's the order. Chlorine, NO2, F2, NO, and CH4. A. Okay, next one, 118. Complete the following. Because real gas particles have attraction for one another, real gases act most ideally at STP. Could be. Let's see if there's a better answer though. We assume gas particle, wait a minute. Because real gases have attraction for one another. Okay, B, we assume gas particles have negligible volume. That doesn't have anything to do with it. 1 mole of an ideal gas at STP has a volume of 22.4. That has no bearing on this postulate. Real gases have attraction for one another. Real gases act more ideally at higher temperatures and lower pressures. That addresses the question. Because real gases have attraction for one another, you need higher temperatures and lower pressures. So D is the answer for this one. All right. 124. Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? Okay, remember the van der Waals equation. I don't. But it had a pressure term and it had something over here. I don't know, something over here. And then it had a volume term and it had something over here. Negative or positive, I don't know. And then nRT. So the correction values here were necessary because real gases either repel or attract each other. Okay. So the answer to this question is the situation where the gas particles do not attract one another or repel one another. They have no interactions whatsoever. So how do we do that? The best answer is to look for non-polar molecules or gas atoms for that matter, non-polar and small, right? Smaller volume means more ideal because that means with smaller volume for the molecule, there's more distance out here with nobody occupying. Okay, so which ones are polar? Well, this one has a polarity. It's polar in that direction, right? So we can throw ammonia out. Ammonia definitely needs a correction. Now, the corrections can exist for any of these, but we want the lowest correction. Okay, so oxygen, chlorine, and hydrogen, those are all nonpolar molecules. Which one is the smallest molecule? That's the key. It can't be chlorine. Chlorine is huge. Oxygen is a little smaller. Hydrogen is the smallest. It would have the smallest correction factor. The other thing that I didn't mention is at the same temperature, which one of these molecules is going to be moving the fastest? Well, according to the root mean square calculation, the fastest one is going to be the smallest one, right? And if the molecule is moving really fast compared to its competitors, then there's going to be less time to interact when it does hit something. And that means less interaction, less correction required. All right. Let's see how many more of these we got to go. Here we go. This is a good one. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. So what's a manometer? A manometer is a modification of the barometer to measure gas inside a vessel. So in this particular manometer, we have 2.34 liters here. Inside that vessel. So the manometer, in this case, reading the problem, you see that the mercury level in the arm of the manometer attached to the gas sample is 24.3 torr lower than that of the arm open to the atmosphere. So in this particular manometer, it's open to the atmosphere. Here we go, like this. Okay. That's open to the atmosphere. All right. The mercury level in the arm attached to the container is 24.3 torr lower. Like this. 24.3 torr, which is millimeters of mercury, lower. So that difference, that delta height is 24.3 torr. All right. We're also told that the atmospheric pressure is 1.23 atmospheres. So bearing down on that is 1.23 atmospheres. What's the pressure of the sample of gas? This is where it pays to look at the answers. The answers are in units of torr. So rather than convert this to atmospheres, let's convert that to torr. So 1.24 atmospheres converted to torr. We need a conversion factor, and that's 760 torr per atmosphere. So 1.24 times 760 is 942 torr. That's atmosphere. Okay. What is this gas doing? It's pushing on this. It's pushing hard enough to overcome two things. It's overcoming the atmospheric pressure plus the difference in these two levels. So the pressure inside here is equal to 942 plus 24.3. Let's see. When we add those together, we're gonna have to throw that one out anyway. So that would be 669. I did something wrong, didn't I? Let me check my calculations. 24.3 torr here, yes. 1.24, 1.23. $935. Okay. $959 torr. There it is. Okay. This is one where it helps to draw a picture. Let's see. Okay. So that's it. And we can go back to number 58 that we skipped earlier. Because 58 is going to take a little time to do.